Good afternoon, ladies and gentlemen, and welcome to this special pre-show webinar edition of the Solar Power International Education Program. Today's session is entitled The Enernet. Doing for electricity what the Internet did for information. Making today's presentation is IEEE, IEC, and US-GBC member and president and co-founder of the eMERGE Alliance, Brian Patterson. Brian is a 30-plus year veteran of the electrical and electronics industry, has an extensive technical and work history in electronics, fiber optics, and building electrical system technologies, and holds multiple patents in those fields. He is a U.S. National Council LVDC delegate to the International Electrotechnical Commission, a member of the Institute of Electrical and Electronics Engineers Standards Association, the IEEE Power and Energy Society, the Continental Automated Buildings Association, the Power Supply Manufacturers Association, and the UL-NEMA eMERGE Ad Hoc NFPA National Electrical Code Task Group on DC Power. Some of you may remember Mr. Patterson as a featured speaker at last year's Solar Power International, and he returns this year to SPI 2016 as a featured speaker and lead facilitator of our new Smart Energy Microgrid Pavilion. So please welcome Brian, who will speak today on the subject of the Internet. Brian.
Thank you, Greg. And after that wonderful introduction, I almost can't wait to hear what I'm going to say. But seriously, before we get started, I wanted to take just a moment to tell you who the eMERGE Alliance is and what we do. Simply put, we're an open industry, non-government, non-profit, member-operated application standards group working in the field of inside the meter, some would say enterprise level, microgrids. Our focus is on the inclusion of direct current technology in such electrical systems, whereby the net result improves one or more of a variety of system characteristics or results. Since time is limited today, let me suggest you visit our website to learn more about eMERGE, including how to become a member of the Alliance. The other thing I wanted to make sure of is that I fulfill the requirement of having time for questions. So I'll ask you right up front. Do you have any questions about my presentation? Just kidding. But seriously, if you do think of a question or two along the way, please jot them down in the Q&A box on the website here. And if I don't cover them during the presentation, we'll try to answer them at its conclusion. So with that, let's get started. So first, I use the word Enernet, that's with an E, in my title. And a lot of people think I misspelled it. But what is the Enernet and why do we need it? Well, you won't find the word Enernet in the dictionary, yet that is. But I first ran across it being used by Bob Metcalf in a lecture series entitled Enernet, Internet Lessons for Solving Energy. You may know that Bob was credited with the invention of Ethernet, a bidirectional local area network exchange protocol that ultimately led to the development of the Internet. I couldn't help but latch on to two key ideas from Bob's discussion of his Internet lessons. First, that the logic of the Internet's development held so many parallels to what was starting to take place in the electric power field. And second, Bob, now just turning 70, was in the process of reinventing himself by applying what he has learned about the Internet and how it developed to the energy world. I, in fact, was in the process of doing the same thing, so I decided that Bob's direction was one that I'd be pretty smart, if you will, to follow. The field of electrical energy today has its challenges. Pick your favorite word or phrase about electrical systems, and you can schedule anywhere from a week to a year or more of conferences on the subject. But more simply put, we have issues, electric power issues, and they are systemic and generally exacerbated by the current centralized and unidirectional construct of our power systems, both in buildings and in the grid. The challenge is that we need more power. We need less use of fossil fuels. We need more socially acceptable ways of physically increasing the content and capability of our power systems. We need to directly address the problem of system resiliency. And finally, We need to address the problem of universal access to electricity, the primary currency of civilized progress. In essence, we need to change the way we generate electrons, mostly by radically increasing the use of clean renewable sources like solar. We need to change the way we move them around our increasingly cluttered landscape in a less invasive, and some would say less ugly and imposing way. We need to encourage the employment of both public and private resources to aggregate and manage new and massively distributed resources of power. And finally, we need to support an increasingly technical use of electricity in our increasingly electroactive, real, not just virtual environment, both on and away from the so-called grid. All of these problems have solutions, both technical and social. And surprisingly, perhaps even fortuitously, there are some common threads interconnecting all of them. The common goals include using clean renewable sources, easily integrating big and small systems, facilitating non-synchronous production, transport and storage and use, all while reducing waste, improving reliability, increasing resiliency, and improving the economics and ease of deploying electricity assets. The common solution thread includes adding clean renewable sources such as solar, wind, hydro, fuel cell, etc., combining massively distributed with bulk centralized sources in single systems, integrating distributed energy and storage capabilities more easily, increasing the use of non-synchronous or digital DC power, using a resilient self-healing mesh network of interconnected grids and microgrids, opportunistic distribution and modular deployment of systems, and allowing self-determinate and semi-autonomous operation of these systems. A massively interconnected hybrid electric microgrid can help us take a giant step toward addressing all of these problems in parallel, simultaneously. Such an approach will complement, if not rival, the accomplishments of our beloved Internet and our increasingly smart grid. I believe the Enernet will do for power what the Internet did for information. It will unleash a vast and indispensable potential for civilization and progress in the 21st century by creating a truly sustainable and resilient energy network that will one day interconnect the entire world, just like the Internet. Today, 70% of all data is created, stored, and used in distributed devices like our smartphones, tablets, and laptops. Regrettable at the same time is that less than 3% of our power producing and storing assets are spatially distributed. As a result, buildings today are the rough equivalent of vulnerable dumb terminals in an old mainframe computer system reminiscent of the 60s and 70s in the last century. But interconnected building and campus level microgrids can change that and allow us to reach similar levels of distributed capability in the power domain, keeping in mind that close to 70% of all electric power is used in those buildings. So just what would all this look like? In the new Enernet, it begins with residential microgrids that will accommodate islanding and grid-tied modes, and that will use smart transactional controls and Enernet interconnection protocols to access and interconnect with all other parts of the Enernet, allowing them to be interconnected with other buildings in local area networks, or better known as campus and community microgrids. Commercial microgrids will be similar, but typically on a larger scale. They too will accommodate multiple power sources, multiple loads, multiple forms of electricity, and allow islanding and grid-tied modes using smart transactional controls and Enernet interconnection protocols. And likewise, they can be Ener-connected or energy connected in groups of buildings, in commercial campuses, business parks, and even mixed-use community microgrids. These primary microgrids can then be further networked into wider area, utility, and private provider Tier 2 microgrids that have slightly different interconnect requirements and protocols from those in the building microgrids. And finally, these wide area microgrids can be interconnected to the Tier 3 bulk power grid. Functionally, this level will be similar to the role of the so-called cloud in the Internet, ironically at times being a cloud for clouds, if you're using solar, that is. And there you have it, the Internet, not all that surprising and strangely familiar. Enernet, Internet, get the connection? I bet you do. And that's because it has combined what we know, both old and new, about power and some key virtues we have learned about the Internet, like access to quality. We can democratize power just the same way we have democratized information. Information is power, but the information with power, oh, the places we'll go. It's a bottom-up structure, power by and for the people. It requires transactive cooperation, a powerful way to say, let's make a deal. And it's self-organizing and self-healing, thus incredibly resilient. Remember Y2K? Frankly, I don't. Creating a semi-autonomous and level playing field in a system this large and diverse in operation will require some new physical and transactional frameworks. But the emphasis here is to accomplish this in a minimum of complexity and a maximum of self-determinate operation. Interfaces, gateways between subgrids will be largely standalone and not require hierarchical intervention. The focus on centralized monitoring and perhaps tolling should not be used as a reason for centralized authority and control. But when we accomplish this redefinition of electricity, this Enernet, we will have successfully transformed the power world and set the stage for perhaps a century of progress by civilization. The Enernet will increase the use of clean energy via massively distributed renewable source access. It will improve reliability and independence and security of our electrical energy systems. It will maintain the intrinsic value of the bulk power macrogrid while improving the ability to provide high-quality power to advanced buildings while allowing remote, low-cost electricity in underserved markets around the world. It will also provide open and horizontal environment for energy innovation, new applications and business models yielding improved energy production, storage, and use. And it will lower the risk of future investments in power infrastructure. Historically, controls have been based on hierarchical centralized systems requiring human oversight and intervention. But centralized, human-in-the-loop control, so to speak, is not sustainable going forward, as the number of data paths, interconnection points, and control points is growing astronomically and becoming exceedingly complex with decision rates exceeding human capability. Imagine a system with billions of energy nodes and trillions of data streams. A transactive framework utilizes a system of economic and control mechanisms that allows the dynamic balance of supply and demand across the entire electrical infrastructure while simultaneously ensuring system reliability and stability. Different framework parameters can be defined at the interconnection points between nodes within this new power network. The Enernet will increasingly employ the use of new and various deployments of the Internet of Things, while allowing humans to set policies, regulations, values, and other discretionary aspects of the network's decision-making capability. One example of a system view of all of this uniquely shows itself in a new set of tools recently developed by Power Analytics, a long-standing provider of comprehensive power engineering tools and services. They are taking their extensive knowledge and experience in military and datacom critical power systems and applying it to the broader marketplace of public and private grids and microgrids. The real issue with the creation of the Internet is timing. The practical creation of the Internet took 40 years and started before most of us realized what was bringing it about or how it was occurring. The Internet will take about half that time, at least that's my prediction, mostly because we have the Internet to help us and its accelerating capability and development. Whatever the timing, the process has definitely already started, and its pace is accelerating by my observation every day. So before you know it, we will have produced a flexible, clean, efficient, resilient, affordable, and sustainable energy infrastructure that does for power what the Internet did for information. I hate to use a word that to some connotes no work, but yes, this system or Internet is inevitable. And perhaps better yet, it will allow the combination of the two systems, that is the Internet and the Internet, to provide a new world of electroactive environments in the physical world that rival those we can only dream about today in the virtual world. And that new world will increasingly rely on the native form of electricity, direct current, and mostly as used in network topologies of interconnected microgrids. But why DC microgrids? Its increasing significance can be traced to the following drivers. First, the use of natively DC power sources, for example, the success of solar, wind, and recycled energy. The use of rapidly advancing battery technologies in buildings and vehicles is all based on natively DC storage. Non-synchronous DC multi-source coupling and busing is simple, low cost, and more efficient. The ease of solid-state digital or DC articulation of power means efficiency goes beyond Ohm's law, if you will. Increasing use of digital electronic loads, most of which are low voltage and safer, and the desire to simplify improves its reliability and lowers the cost of overall system electronics. But power, like data, needs to be organized. There are different formats for electrical power, AC, DC, with different characteristics like frequency and voltage. So conversions will need to be accommodated, but conversions do waste energy, so the fewer the better, and even better when done at the right places in the system. The use of native DC is inherently more efficient than converted AC in most modern electronic devices like LEDs, home appliances, and variable frequency motor drives. But that basic efficiency can be leveraged in microgrids that couple sources, storage, and loads all in the same local power network. But there are some barriers that need to be addressed in order to realize DC's full potential. Some are more illusion than real, so let's acknowledge them first. Not as safe as AC, you say? The actual tests and empirical data supports the facts that both forms of electricity can be equally dangerous. Generally speaking, it has been shown that the voltage is the largest determining factor in electrical danger. AC voltages are generally expressed in RMS terms, while DC voltages are expressed as peak voltages. This means that AC peak voltages are actually about 40% higher than the expressed voltage level of a similarly expressed DC voltage. Not good for long-distance transmission? This is based on the mistaken belief that frequency, the distinguishing difference between AC and DC, affects wire loss. But a review of Ohm's law shows otherwise, since it does not contain the frequency factor. Once again, it is simply voltage that makes the determining difference, as lower voltages raise current and multiplies the effective wire resistance. Being able to step up or down DC voltages electronically has essentially eliminated this difference. Thicker wires needed? This is a different way of expressing the same issue. The assumption is that you cannot raise the voltage for transmission, and the only way to reduce wire loss is to reduce resistance by increasing wire size. But modern DC voltage conversion has all but eliminated this difference between AC and DC, as power electronic conversions can perform the equivalent function of an AC transformer, often at lower cost factors. But the real ones are that there are gaps in standards and codes. Perhaps most present codes and standards are written for AC power and reflect historical, not contemporary applications or technologies that use cases, especially microgrids or an Enernet. Generally, equipment safety or test-oriented codes and requirements are not system or application specific, and new and revised standards are developed slowly. The National Electrical Code, for example, has a 3 to 6 year cycle. Product commercialization usually waits for standards definitions. So these are the problems that my organization, the eMERGE Alliance, is working to solve by providing vanguard standards and coordinating our work with the IEC, the IEEE, the IET, NFPA, NEMA, and other critical standards development organizations. We also work to promote the development of a strong OEM supply base who can help fill the gap in providing industry knowledge and contractor and trade training. Of course, the end game is to grow market volume to achieve competitive pricing. Also, as part of our work, eMERGE and its members have been involved with nearly 100 early form microgrids and nanogrids, the latter term being used for subsystems within a microgrid that include key microgrid assets. These microgrids have been used in buildings from banks to corporate offices. From companies like PNC Finance, who is literally banking on net zero microgrids, and here's an example of one of their bank branches in Fort Lauderdale, Florida, that's using a DC microgrid, to Quicken Loans, who is lending a hand in demonstrating the capability of DC and digital lighting systems. To the state of Michigan, who's sparking a new level of building performance in Flint, Michigan, at their Treasury building that now uses DC lighting. And to the home of one of eMERGE's founding members, who is showing us what's next in energy systems. This is a center that now is about 80% converted to the use of 380 volt DC, along with a lower distribution to sources at 24 volts. And by companies like Pitt, Ohio, who are moving their building energy technologies just as fast as their freight, using forklift charging stations that are now DC and solar powered. And to the nation's utilities like Duquesne Light, who is demonstrating the utility of combining the use of both AC and DC electricity in their own systems. And to the poster child of all microgrids, the NTT Facilities NETO-funded demonstration project in Sendai that was the only grid that continued to operate in the aftermath of the 2011 tsunami that struck central Japan and devastated most of the terrain around it. But if you really want to see a microgrid, a DC microgrid firsthand and operating up close and personal, come to this year's Solar Power International, where you can meet and talk to some of the key industry innovators in this field. During the 3 days of the show, there will be a full day of education track on smart energy microgrids, over 30 in-pavilion technical presentations, live operational demonstrations of the microgrid, which will be powering the pavilion with live and stored solar energy. There will be a grand opening ceremony, we call it the plug pulling, where we'll go on and off grid intermittently. And after hours, there will be a networking happy hour where you can socialize and meet with some of the industry experts and companies who are participating. And there's much, much more that will be going on in the Smart Energy Microgrid Pavilion. Well, I hope this gives you some idea of what the Enernet is and how it fits into and empowers the new 21st century energy age. So now I'll turn it back over to Greg and see if we have some questions or comments.
Yeah, thanks, Brian, for going over that. That was great. We do have some questions from the audience here, and if you have any, there's a Q&A section that should be in the webinar area, or just chat them through us, and we'll try to get to all of them here, and if we don't reach them all, we'll make sure to send out a corresponding email along with the slide deck and video of the webinar too. So first off, Brian, thank you, Tom, for sending in your multiple questions here. That's greatly appreciated. First off, he asked, how does energy, water, and wastewater utilities, how will they be integrated? And then what are Energrid advocates, what are they doing to help push to actually have this added to the grid of the future?
Okay, that's a pretty broad question, but let me see if I can take a shot at it. Well, first of all, we talked largely about electric energy. We don't talk about the way that could be created if, for example, you have a combined heat and power system. Many of you know you can generate a lot of electricity, biodigesters, all kinds of either waste or wastewater facilities that can be combined in multi-mode use that will reduce the cost and increase the resiliency and minimize the environmental impact of energy systems in general. So at the community level, whether the utilities are combined in municipalities or whether they're operated as independent private organizations, by creating more of a network topology for power, it will allow a much greater cross-utilization of the capabilities of these normally municipal operations. So a lot of the first talk about microgrids it has been at the municipal or community level. And I suppose the other end of the spectrum is all the way down to the individual private home. But now some corporate folks are getting involved in realizing that actually the production of energy at their own site gives them a lot of benefits that they didn't otherwise appreciate until they fully understood what they could do with that. So I hope that answers part of your question. The second part of your question was?
Just what are Enernet advocates doing to help push this?
Okay, so we attend, as you see, conferences like Solar Power International, Green Build International. We'll be at Consumer Electronics Show this year. We're at Light Fair in the lighting industry, advocating this kind of open transactive system in energy. We also spend time with other energy advocates, the Alliance to Save Energy, some congressional caucus, advanced building or high performance building caucus, et cetera, that we try to explain why we want to move to a more network-like or mesh network-like structure, which allows, we think, the acceleration of the participation of distributed energy systems like solar and other ones that you mentioned to participate on a more level playing field. So we are out advocating as well, along with them. For example, one other example, just off the top of my head, we are working with the Alliance for a Sustainable Colorado. They have a 6-story building in downtown Denver that they're in the process of using as a test bed. We're converting it over to a mesh network DC topology that will demonstrate to the folks in Colorado and elsewhere. I'm sure it'll be open to the nation and maybe probably internationally to go visit and see exactly how this building will operate in that mode. Keep in mind that when you do a microgrid at the building level, it's sort of like what a personal computer is to the internet. It's a private system, but it can be put into the network and become a transactive node in a much, much greater network. So whether you're using it for private power or you want to sell power, that's where the transactive nature of this type of grid comes in. Next question, Greg.
Thanks, Brian. With this connected grid and all the latest technology that we're trying to integrate and make that happen, what are some of the cybersecurity issues, and more so, as far as security, do utilities need to be aware of, or what are they being added to make sure that there isn't a breach in some way?
Again, this is probably the subject of a few whole conferences, maybe for a week. But cybersecurity is kind of the result of having moved forward on the internet, maybe a little bit faster than people realized. Well, they would be open to interference, I'll call it, from the outside in terms of security. But one thing we've learned with the internet, even though now encryption, and you've probably heard all the way through to the fact that companies like Apple were reluctant to give up their encryption protocols to even government agencies. But in any case, there's been a sort of a catch-up. But one of the nice features about any system, whether it's the internet or the Enernet, is that you can disconnect from it. So a first-level security in any cyber attack is to prevent entrance. And the simple way to prevent entrance is to disconnect, essentially, so that the attack is limited in the way that it might attack the whole system. And that really applies to whether it's a man-made kind of attack of the system or whether it's a natural disaster. The ability to it's such a disaggregated mesh that it has the ability to kind of isolate the problem very quickly and prevent the whole system from being taken down. That's kind of a simple answer to a very complex question, but I don't think there's any magic in whether we do things in the internet or we do it in a more traditional view of the smart grid at the bulk power level. We all have to keep in mind that cyber information, if you will, that will be used to control power systems needs to be protected with the utmost care.
Thanks, Brian. So it comes from Jim. Thanks for sending in the question. So yes, how do we get utilities who are comfortable with the way they do things today to look at a new way of doing things? So how do we get them to transform to that? And also, where is that motivation coming from? And the final part, I know it's 3 parts here. Where's the money going to come from, or where is it coming from today to make this happen?
Yeah, I'll answer the last one first, and it's sort of like, where do we get the money to put in the internet? I can remember days when the only, besides the power line and the telephone line to my house, originally the cable or cable TV companies were granted an exclusive also. And you know, nowadays those exclusivities have been removed. And not only do we have multiple ways of doing telephony, but also communication, security, and a whole bunch of other things that people said wasn't going to be economic because it required more wires and more companies and more, security and so on and so forth. And that just wasn't true, because one of the things I think most people underestimate in new technology is the value creation of what the technology can do. And although most people off the top of their head won't think of new apps for electricity, I am a personal believer that if we make a system that essentially unleashes, in this case, solar energy, which is essentially, once you invest in the infrastructure, a unlimited and free fuel source, that we're going to find more and more uses for electricity. Now that sounds antithetical to the whole effort of energy efficiency and conservation and so on and so forth. But I do pose the challenge to say, if energy is produced or electricity is being produced in a clean and economic way, such as through solar, why would you need to conserve it? Why not use it to produce wealth and well-being in society? So in a certain context, what I see happening is electricity will be used for more things that create more wealth, more good, more health, and well-being around the world, and that's what's going to essentially pay for it. It's the value creation process. Today, because of the way we use and make and distribute electricity, the value creation essentially stops at the meter, We have an interconnected the other side, the use side, and what is now being developed as a prosumer side behind the meter applications. But once we do that, the value creation will go up both for the utilities as well as for the private enterprises and consumers on the other side of meters. So I personally have no major concern that there'll be value created that will pay for new technology just the way it did in information. Second part of that question was about utilities. How do we convince utilities to participate? Yes. I have to say that I'm working with a number of utilities who maybe they're self-enlightened on the whole subject, but they seem very willing to participate because, as I said, there's value to be created, and there's no reason why utilities wouldn't participate in that value creation process, whether it's for combining power sources, leasing equipment, whatever it gets to be. Utilities are no different than any other enterprise, and given the right incentives from the regulators, I believe that the utilities are probably among the best possibility to participate in some of these new market areas. Although I think also there'll be a lot of new companies that participate and equipment manufacturers that couldn't before because the system will be enlarged throughout the world. Some of you may not know that 25% of the world today has no electricity. So there's a huge market there, and another 25%, making up a total of 50%, have a shortage of utility and essentially are subject to rolling blackouts and other demand reduction efforts that keep them from having electricity on a regular basis. So there's lots of market opportunities still out there in the world as well.
Great. So that's actually a perfect segue into our next couple questions here. One of those being, how do these low-income or newly developed areas, how do they start off with something like the internet and making sure everything is connected in the grid?
Sure. Well, one of the first things is that we're trying to create standards for the development of what we'll call these local microgrids or individual microgrids, maybe one home or one hut at a time, so to speak. And that's very important. There's lots of people out there trying to help in these areas in Africa and South America and Asia, where there's this tremendous underserved population. But without standards, we run the risk of putting out systems that eventually don't connect together and add up to a power system like we enjoy here in North America. Some of you may not realize, and this happens to be the 100th anniversary of DC Microgrids in America. In 1916, if you lived on a farm or had a rural home in central United States, you didn't have a utility that you could go to for power. And there were over 3 million homes and farms in America that had their own power systems. Interestingly enough, they ran on DC power, most of them 32-volt DC power. They were used gasoline or fossil fuel generators because there was no solar developed at the time. But essentially, the rest of the system was much like we're promoting these days, in that it had batteries. They used droop control to kick on the invention of the electric start motor, so they could actually start up the generator remotely and monitor the need for generation based on the droop of voltage out of the battery stack. But basically, this is a pathway or a roadmap that was created over 100 years ago and eventually rolled up to what we have today in the United States, which is a national grid. But we still need to and want to accommodate people who want to produce their own power, live off grid, or what have you. So in those remote applications, it's likely to develop much like it did in central United States, and that is that it'll start from the bottom up with these microgrids. Now, in order to make sure that eventually those microgrids can be interconnected into the Enernet, just like today in many of those places, by the way, they're already using cell phones and personal computers and have to walk for miles to get them charged because they don't have electricity. they are using the protocols, the international protocols of communication. They can connect up to the internet. They can't do that with the electricity because those standards in many of those countries and regions of the world don't exist. So that's another area in particular that eMERGE Alliance has teamed up with the IEEE. And if you're interested in helping us, we have a committee, and if you're an IEEE member, it's the 2030.10 committee that's working on remote access microgrid standards for the underserved world population. With a mind that even if we create them at individual homes or hut level, that they eventually, over time, could be interconnected into community microgrids and then up into mega grids, just like we have in the States here.
One more question here, and then we'll get to David. We'll get to your question about the state policy. So this is all fairly new, and some of this that's happening right now, it's still a little bit of unknown territory. And throughout the presentation, you alluded that there will be some new technologies that we don't see right now that will emerge. What are some technologies that we do see right now that are cutting edge, that are really changing the landscape of the internet? And what are some that you might even project that could come into play in the next year or so?
Well, one of the simple ones, and the wave, it's more like an ocean that keeps crashing on the beach of progress, is solar power itself. There's been tremendous advances in solar generation, both in different types of arrays and built-in PV and BIPV and so on, that I think is really accelerating the opportunity to bring solar into the power system in a major way, both at the utility scale and at the individual private enterprise scale. Secondly, of course, is storage. I mean, there was very little need to or capability to interconnect computers until we had data storage. So if you imagine, because a lot of people ask, where do we put the batteries in the system in order to store power so that we can use these intermittent capabilities like solar and wind and so on and so forth? And I simply say that storage is something that we'll probably need at a number of different levels. Sometimes we just need a little bit of ride-through time so that we can switch or engage another source or what have you, like you do in a data center with a backup UPS or generator. And sometimes we'll need quite a bit of storage to back up maybe VAR support at a substation, to use an extreme at the other end of the spectrum. So storage, like data storage, power storage, will probably populate many, many different places. And I think this is an area where technology is still blooming in a way. You'll see many, many new things at Solar Power International on battery storage and other storage means. And I think those waves of storage technology innovation are still just starting to reach the beachhead, and we'll see a lot in the next 2 to 5 years in storage, both in terms of technology and in and the economics of storage. I can remember, by the way, when I started computing that about 1 gigabit of storage cost about $300,000 on a computer system back in the 70s. Today, I just saw the new Samsung, I think it was Note 7 or something, phone, had 256 gigabyte, and they were giving it away for free as a promotion to buy the phone. So that tells you how much it's advanced in that period of time, and I think the same thing is going to happen with power storage.
Okay.
I hope that answers the question somewhat.
Yeah. So this question comes from David. It's more about the state policy. It's a two-part question here. So first, what are the key policies that need to be in place at the state level that maybe aren't right now, that should be pushed in? And then I'll follow that up with, what can an advocate do to help make sure that that policy is being put in place at a state level? I
would, again, this is a very complicated question in a way, or at least a detailed one, maybe not so complicated, but detailed. I would recommend that you look at what's happening in New York State with REV, That's a program that New York State has started to sort of encourage an increased use of distributed renewable energy and innovation and cooperation between private and private concerns and utilities and public municipalities. And also in California, two states, either side of the country, have slightly different motivations and a slightly different approach to things. But if you watch what's going on in California, watch what's going on in New York, I think they're the more progressive in terms of the way they're addressing the regulatory questions and issues. But I would say they're not alone. There are other states that have started to address it. It is something that I think shares a responsibility both at the federal level with the Federal Energy Regulatory Commission and at the Public Utility Commissions at the state level, where essentially when we enable millions of prosumers who were not stakeholders in the regulatory terrain before become stakeholders, they need a voice. Now, with respect to that, recently, and the comment period just closed, so I won't say that you can still submit a comment, but the Federal Trade Commission has also entered that arena, much like they did when telephony regulations were being questioned back in the 60s and 70s, to look at having a sort of a level playing field for consumers, that you can participate in the energy commerce, if you will, and that it's not strictly, protected for a unique set of companies like utilities, what have you. Again, I'm not advocating anti-utility because I think that utilities are an important and will continue to be an important piece of the whole structure. And like I said, they will provide the cloud, if you will, and the capability of both transmission and most of the distribution assets in this whole equation. And as they themselves develop new business models at the user level, they will become a part of all three tiers of this system. So I think there's plenty of opportunity for everybody there.
Okay. This question comes from Tom. He said, "Are there any utilities that you're already working with to do demonstration and pilot projects? And then, are there any utilities actually beginning to start planning this transition right now?"
We've done some. I'll mention the ones that I know of from the eMERGE perspective. We've done some work with SoCal Edison. I'm happy to say that they were among the first to get involved with us, and they're out in California. And they have experimented with a number of microgrids at the user level. I'll call them behind-the-meter microgrids in education and other buildings. But also Duke Energy here in the East. They have been involved and continue to be involved with a number of different pilots. We work with Detroit Energy. I mentioned Duquesne up in Pennsylvania. Detroit Energy, obviously, in Michigan. And I'm probably leaving out a bunch of others that work with us. But I think they understand that the movement in the prosumer direction is one that is going to need to be accommodated, and that they can actually be a part of if they're proactive. I would feel bad if we looked at utilities as anything other than a great opportunity for just an expanded level of participation on their part in the consumer side or behind the meter as well.
Okay, great. We have two more questions before we'll close this out, and we'll send our contact information out after this as well. So if you have any questions, we can correspond.
Or just come to Solar Power International. You'll see us there.
So this question comes from Rocky. Nevada itself as a state is a little bit controversial. So it said Nevada Energy is hindering rooftop solar in Nevada with the surcharge. Said Tesla is also a big Nevada player. Why hasn't Elon Musk stepped up with Powerwall?
I would suggest that you probably have to ask Mr. Musk how he's working that. But I think you know, we all have to be a little bit concerned that we don't want the investment that we've made over the last 100 years in our national utility system to go, you know, unrecognized in the value that it has both now and in the future in this Enernet going forward. I think that many of the regulators are trying and searching for ways to keep those investments viable at the utility level, and in a sense protect what is there until we kind of figure out the turf going forward. But I would say that at some point, and I was suggested in that first question about how do we pay for things, that we really do have to look at the potential for value creation in this system. I know when I used to think of my phone as just a phone, I only wanted to pay, back in the day, it was like 10 cents a message unit or something like that. And I know today everybody talks about power as so many cents per kilowatt. But I don't talk about my smartphone that way. You know, it's not even a phone, as you know, my smart device, because it has accumulated so many other valuable characteristics. It, you know, keeps my calendar, and it keeps the pictures of the grandkids or whatever, and it just makes life a totally different experience. And I think power has that same potential. As I said before, we seem to be enamored with information now, and that's great. I love looking at the pictures on the screen. But you need power to do things. You need power to move things. It takes energy to do work. And as we do that work and create the new environment for energy to be more valuable, there'll be plenty of money to go around to pay for not only the successes in the marketplace, but even some of the difficulties. So I would just say that be patient as the regulators, be a little patient as the regulators try to work out the path forward. But maybe you can help them by providing the examples and some of the experience that you see coming out of California and New York and other places that are pushing pretty hard.
Okay, thanks, Brian. One last question here, and then we'll end the presentation. How are electric vehicles and electric grids going to be integrated?
Probably in a number of ways. For sure, electric vehicles are a new load on the system. I think it was projected that probably somewhere between a 20 to 50% increase in the amount of electricity used will go to transportation. And we need to find better ways to do that. And there's a lot of debate about, you know, do you use more energy burning gasoline in an engine or electricity in a power plant? I think there are other solutions, particularly solar and other, that will contribute to that solution and make electric vehicles probably the best choice going forward at some point. In the meantime, electric vehicles may contribute to the ability to make portable storage. I mean, I know I carry my laptop around and it has a hard drive in it, so that's just like carrying, and it has a battery, but you know, as you know, and that's I use that to charge now my smartphone. So in a way, I'm carrying around a power system and a data system and making it more portable. I think as we go forward, a lot more of our mobile assets will come into play in a similar way in both data and energy. I know some people are looking at the rather massive transportation infrastructure we have with trucks. You know, can they be mobile power sources, if you will? Because they do have a lot of surface area and so on that might be employed in harvesting power as they're on the road and so on. So I think there's going to be a great difference. I think by the time my grandkids get to drive a car, they won't have to. That cars will be self-driving. I know that's another controversial subject, but I think that as self-driving vehicles, there will be an ability to use less energy in the car itself and to use the battery capability in the car to perhaps provide some of the support capability that energy needs to make some of its power storage more mobile. So we'll see how that goes, but this is the great thing about the new paradigm in energy, is that we can think about innovations just the way we have in data all these years. Think of the parallels between data and power, and I think you'll find a path to great innovation over the next couple of decades.
Great. Well, thanks a lot for your time, Brian. As we close out, if you do have any questions, I did chat my email in the box there. Otherwise, we will be sending out a recording of this along with the presentation later, probably in the next day or so. So again, thank you everyone for joining us today. It's been great. If you do have any follow-up questions, we're available to talk. Thank you.